So I have still a few minutes, so I'll go through some of the other projects. Next one in line is the equation of states. This project is has been designed in order to optimize the unit cell as well as find the bulk modulus. The parameters in this case are very simple, are the number of images and the lattice constant variation. So a set of single point calculations, geometry optimization calculation will be performed, and the energy will be extracted for each of them. And this is the result. As you see here, there is no minimum. So this calculation is not enough in order to extract correct value for the optimized cell of your system. And this is done on purpose because then we have another project in which we selected another region and in basically another parameter for the optical, for the lattice cell and other value of variation. And in this case, we are able to find a minimum. And here you have information about the method that has been used for the interpolation, the original as well as the equilibrium cell. And also, as you mentioned before in the presentation, the bulk modulus. We don't have a project on variation on the transition state of the NEB, but we still have one for this molecule, formamide. Here as well, the settings are very minimal. And the analysis, we can see the vibrational density of states with the vibration energy corresponding to any of the possible vibration of the molecule. And we can also inspect each mode. Vibrations is usually a project that is used for finite system or for system as you saw before when we have a slab plus a molecule. For a bulk system, it's possible to compute the phonons. In the input parameter, you can set up the supercell shape and the displacement magnitude. And in the analysis, similarly, if you want, in what we see in the band structure, we see the band structure of phonon with the corresponding density of states. Path can be edited, and in this case, it's not necessary to do it in the pre-processing phase, but it can be done at this stage while you are analyzing the result. Next one is an MD, some molecular dynamic project. This was done with MD ASE, which is one of the two algorithms that we have at our disposal when we want to compute molecular dynamics. And we use this EMT calculator, which is, well, it's not as precise as Siesta or Quantum Espresso. Obviously, this is used just to do some test, which is what we wanted for this specific case. And in the analysis, we can see all the information that are provided. So we have time series where you can see the energy contribution to the system. So kinetic, potential, potential only, temperature, total energy. Here there is no pressure because we are using EMT as calculator, but if we use Siesta, we also have information about the pressure of the system. And we have a section on statistical properties, and in which you can basically look up at mean square displacement, diffusion coefficient, if it's meaningful in the system, root mean square displacement, velocity correlation function, power spectrum, so many things, as well as a radial distribution function. So this is a fast overview. Obviously, I'm not going to go into the detail of what each of these means, obviously, because you take much more time, but it is to give you an idea of what information you can have, because some of those might be something that that you are familiar with. Something I didn't mention, I forgot, is to say that if you go in the parameter widget, you can decide the kind of simulation that you want to say, the ensemble. So you want to perform an MVE, MV, or MPT. And if you select each of those, each of them. Then you can further specify the parameter of your simulations, including number of steps, initial temperature, final temperature, depending on the selected algorithm. Interface analysis tool, as I mentioned briefly in the introduction, is a method in order to calculate the energy profile of two systems, one displacing with respect to the other. And this is the settings widget, in which you can set up the minimum distance, maximum distance, number of steps. You can also include some displacement in some shifting plane and some rotation in the molecule during this process of during the process of basically putting the two systems together. And the analysis is a profile curve. So each point corresponds to a DFT siesta calculation in this case. And the distance is the distance between, in this case, the molecule and the surface. And from these informations can be extracted, more specifically, force field for classical MD can be extracted from this information. We have then two transport projects. If you want to know everything about it, please check our previous webinar, in which my colleague Irina made an amazing job and explained each of these sections. In this case, I just tell you that we can calculate the classical IV curve, a different voltage, and transmissions. The effect is not visible here of the electrodes as well as the scattering region can also be visualized. Finally, we have a new project that has been is new in this new release of ASAP. It's a project to calculate the Fermi surface. So if we go in the analysis, we got a lot of information. Again, maybe we need like 15 minutes just to go through all of them. Basically, what we see here is a representation of isosurface at a given energy in 3D, 2D, and on the right you see the band structure related to this system. So many things here. You can play with many numbers, change the ISO value, change spin up and spin down, and see how the image is changing. And look exactly at the Fermi energy value. What is the isosurface within the cell? Obviously, this is, I didn't specify, but it's a kind of project that is available only when you have periodic system. So I went through all this project. It was a very fast overview. Thank you all for attending this webinar, and see you soon to the next one.